And I am mainly working in the neuro domain, but of course we are also doing stuff with lungs and with other body parts, with all kind of diseases, with 60 people. So if we're talking about image processing in the neuro domain, what we want is to get quantitative biomarkers out of the data. And with quantitative biomarkers, you can think of brain volumes, so the amount of white matter, gray matter, CSF, or the volume of different structures, the size of the hippocampus. But you can also go to a more complex quantitative analysis like voxel-based morphology, where you can see that if there is in the brain some expansion or shrinking of matter. Of course, there is perfusion, so we can see if there is more or less blood flow in a part of the brain. And with all these developments, we use AI nowadays, but also just the conventional machine learning concepts. Interesting, I will show later some examples. Functional MRI you can also do, so you can see activity in the brain. That's also, you can do, you can let the patient speak or move his hands or just lay still, and then you get activity in the brain, location of the activity. And of course, you can also detect microbleeds, infarcts, etc. So let's, I'm here, by the way, because the last years I'm working closely with Irene on several projects to try to apply these tools also in the field of the craniosynostosis. That's not easy because most tools are developed for adult brains, for adults. Also, the craniosynostosis data is, you have problems. The brain of children looks different in an MR scan than the brain of adults. For example, when they're very young, with the myelinization of the white matter. Also, we have, of course, a deformed brain and skull. That can be a problem. And another problem is that a lot of times the image quality or the number of slices is not perfect. There are also artifacts in the image, so it gives us a lot of problems, and not the standard tools are not always working with these data. So I will just give you a short impression of what we are doing in this field and mention a couple of tools. What can we do? What are we working on? And then you have to think about tissue segmentation. So the intracranial volume, the amount of gray matter, white matter, CSF. But we can go further. You can also divide the brain into smaller regions. I will come to that later. Detection of the lobes, DTI is of course an interesting possibility. And we are currently working also to detect or segment label the ventricles, the big ventricles. Yeah, okay. Also starting then with the hype word, deep learning AI network. How does it work in the imaging field? Well, there is input. On the left side, there are a lot of layers connected. And all those layers do a kind of processing on the data. Normally just going to a lower resolution, averaging some parts of the image, looking more to edges, looking more to intensities, and at the end you get an output, and the output can be a decision, so like it's a pig or a dog, or it can be an image again, like a label data, for example. So we use this for to segment the brain of the data into gray matter, white matter, and CSF. And of course, you have to train the network. And luckily, in the image processing field, we are building up a lot of data. For example, we're also working on the Rotterdam scan study where we scan adults. We started already in 2000. We have about 24,000 MRI scans with all the processing with it. So we can train our networks with that data. And with the tissue segmentation, you get these results. So you put in a T1 image and a T2 image, and you have the CSF, the white matter, and the gray matter. This is not, by the way, a child. Another tool is Deep Surfer, a free surfer. It's a tool that exists for a long time already. There are version 7 now. It is a tool just with conventional machine learning techniques, and it's doing a lot. For example, skulls. It starts with the skull stripping. So just get out the skull from the image data. doing all kind of corrections, and then again the tissue segmentation. But it's doing more. It's also labeling the subcortical areas, and it's also subdividing the cortex into a number of regions. And there are 2 atlases, and you can so you have about 34 right and 34 left, or you can also have about 85 left and 85 right regions. And from all those regions, you can get the surface, the volume, the curvature, and the thickness. So that you see in the middle. It's like I said, those tools are not automatically working on children data or on cranio data. So there is also now a couple of years an infant free surfer. So they replaced several parts of it, they improved several parts of it, and they also add templates of children. So you have to give the age of the child in months to the pipeline, and then you get something like you see here on the right. Again, the same tissue segmentation and parcellation of the cortex. Another tool we use is, for example, for the infant atlas. There is a lot of data available nowadays. It's all collected. This is a nice. We use this tool to divide the brain into the lobes, the different lobes. We couldn't do that with the free surfer pipeline. Now it's working, the infant free surfer, but when we wanted to get this data, not yet. So this is an atlas. From the top to bottom, you see the ages. It's going from 0 months to 24 months. From the left to the right, you see again T1, T2, tissue segmentation, and the free surfer parcellation. And the idea is that you register that to the patient data to segment the different brain lobes, and then you can see the increase or decrease of white matter, gray matter in the different lobes. And finally, here's just one example. The slices it's not so clearly visible, but on the top the T1, then the tissue segmentation in the middle, and down the parcellation of the cortex and the subcortical areas. Diffusion tensor imaging, another interesting tool. You can, with an MR scanner, you can measure on every location the diffusion of the water molecules. And with the standard, you have just one perfusion or diffusion measurement, but if you can do it, for example, in 28 regions, and then you can build up a kind of ellipsoid that says something about in what direction the diffusion is higher or lower. And if there is no difference in the direction, it has an isotropy of 0, and that's normally in the gray matter. If you're in the white matter, you get more elongated profile, and you go along the tracts. You have, in the extreme situation, an anisotropy of 0. And then you can, like you see on the right side, visualize the tracks. You can follow the tracks. You can just go and walk into the direction of the highest diffusivity. And you can also compute later the mean diffusivity and the FA value on every tract, and that tells you something about the integrity of the white matter. And finally, we are working now on detection of the ventricle system, the ventricle 1 and 2. Also not very easy. Here you see some examples of scans we have. How we do this is we use a tissue segmentation from HyperDenseNet. On the left, you see a kind of model of the ventricle system. We register that again, so matching it on the tissue segmentation. We take the CSF, we do some post-processing like connected components, taking the large region, and then we see results like here on the right. It's not always perfect, but we're making some progress lately. And there is some time, I think, so I would like to ask Linda to go a little bit more into quantitative results in the study that we did with the metopic craniosynostosis.
Thank you. I wanted to give an example of how we use these automated MRI techniques. And two examples are studies that we use to gain insight into the pathophysiology of metopic synostosis. So currently the pathophysiology is unclear, and there are two main hypotheses, namely the mechanical constraint and the intrinsic brain anomaly hypothesis. So the mechanical constraint hypothesis states that metopic synostosis is due to a true malformation of the frontal bones, and that this may restrict brain development and also cause the neurodevelopmental disorders with which metopic synostosis is associated. In contrast, the intrinsic brain anomaly hypothesis states that metopic synostosis is due to an intrinsic brain anomaly that results in an insufficient driving force for maintaining suture patency and can in this way lead to neurodevelopmental disorders later in life. So to gain insight into the pathophysiology of both metopic synostosis as well as these neurodevelopmental disorders, we use DTI as well as brain volume measurements. So for the DTI study, we included 46 non-syndromic metopic synostosis patients, all under the age of 2, who are not yet operated. We compared them to 21 healthy controls of a similar age, and we found that there was no significant difference in microstructural properties of the major frontal lobe white matter tracts. And this is if there were a mechanical constraint where we would expect the largest difference given the deformed head shape in metopic synostosis. So we also looked at brain volume in a similar population of unoperated non-syndromic metopic synostosis patients, and we compared 45 patients to 14 controls. We found that there were no significant differences in total intracranial, total brain, total gray matter, or total CSF volume. And this can also be observed in the graphs on the slides. So on the y-axis, we see volume in cubic millimeters, and on the x-axis, we see age in years. Patients are indicated in red, and the controls are indicated in red, and the patients in blue, with the line indicating the best fit. So in contrast to these brain volumes, we actually did find a significant difference in white matter volume, which was significantly smaller in patients with metopic synostosis compared to healthy controls. And this difference was especially pronounced very early in life and seemed to correct towards the age of 2. So it seemed to indicate a sort of catch-up white matter growth pattern in patients with metopic synostosis. And this is especially notable as this pattern of catch-up white matter growth had been previously described in young patients with autism who have a similar white matter growth pattern. So taken together, we found a normal white matter microstructure with pleats against the mechanical constraint theory. But we found a smaller total white matter volume with an accelerated growth. And as this is similar to patients with autism, this may contribute to the neurodevelopmental disorders that are seen in metopic synostosis. So combined, these initial studies using these automated MRI techniques, I think, suggest a generalized intrinsic brain anomaly and have been very valuable in determining better how the pathophysiology of metopic synostosis actually is. I think in future we can expand these automated MRI techniques to both other areas of brain development, but also to different types of craniosynostosis. And I think a major advantage is that they are highly reproducible and that they give us quantitative measures rather than measurements that we do ourselves manually. Thank you. We'd be happy to take any questions.
Thank you very much. Very interesting talk there. Would anybody like to ask any questions? I'm sure there'll be lots there. Well, sorry.
Hi, Lima. Thank you very much. Just quick question. Did you check genetic tests on this patient? Because we have seen a lot of news MADCIS mutation that in our experience are really related to some cognitive problem. And also, I think that you really check very well the age, but it looks like the control was a little bit older than the patient because the myelinization can have big differences related to the age. It can be one of the reasons of these differences. Thank you.
Thank you. We included only non-syndromic patients, and we checked genetic diagnostic results. So we excluded any patient with pathogenic variants. Also SMED6, yes, yeah, because it's associated with neurodevelopmental disorders as well. So we excluded any patients and also any with clinically syndromic features. Regarding the age, we corrected for sex and age as they both are known to affect brain measures. There may be some residual confounding as it was small sample size. So I think it's important to repeat the study in larger sample sizes, but we did correct for it in our analysis.
I understand well. You see similitudes between your result and the results of children with autism, but which sort of autism? Because it will be very important to compare some very caught with an etiology, for example, to understand the mechanism of this problem of the white matter.
Thank you. I think the papers that looked at it were general autism spectrum disorder. So I think it would be important to further differentiate in the future as well.
I know this is a little stone in the building of not operating metopics that is behind all this. But I think what is missing to convince us that would be to compare, to do the same examination in people just after the AFO. Because if doing a frontal-orbital advancement, you catch up this problem of white matter compression, it changes, you know what I mean? To see the place of surgery. I don't know if you still operate metopics in Rotterdam, but maybe you can get MRIs if you're able, if you tell us what to do, places where we still are operated on.
Thank you.
Yeah, I would add to that. It would be interesting to see actually what the surgical has an impact on these measurements, especially if you compare not only the late surgeries by frontal orbital advancements, but especially the early surgeries of endoscopic surgery, because there's still the developmental potential. Yeah. But you haven't done that, right?
Not yet. No, it's an interesting future project, I think.
Thank you. One more question down here. Getting a bit of exercise, I think, today. Thank you, very nice, Nata. Actually, the question is, how did you get the control group? I mean, how did you convince normal subjects to perform the MRI at that age? Or there were normal MRI in patients who underwent MRI for other reasons? That means they are not really normal. Thank you.
Thank you. So we included MRI scans from patients who underwent MRI scans for other health reasons. Charts were reviewed by a pediatric neurosurgeon, and the MRIs themselves were reviewed by a pediatric radiologist. If they both deemed that the patient was healthy and there were no anomalies, either for cerebral anomalies or skull pathology, they were included. Thank you.
Can I make one tiny remark? I think the actual goal of the presentation was not so much on the trigonocephaly. It's just an example. But I think this feature of automated analysis of MRI scans, it's a great tool. It's made especially now for very young infants. And I think that if you're interested in that, there's all these pipelines being developed. And that is, I think, the take-home message. So talk to Henry if you're interested.
So again, in the spirit of collaboration, a show of hands of who might be interested in collaborating and sending a lot of MRIs over to you guys.
Yeah.
There's a few people here all right. Okay. Okay, thank you very much.